Welcome to the presentation of our exciting paper at ARC 22. It is called FPGA-extended General Purpose Computer Architecture, and it's authored by me, Philippos Papaphilippou from Imperial College London, and Myrtle Shah from ChipFlow.
To motivate our paper, we start from comparing existing platforms. Starting from ordinary processors, they are very easy to program. This is because of decades of software engineering research. Therefore, there are mature programming models, lots of libraries, and effective debug and verification tools. At the same time, there are many useful abstractions, such as the caches and virtual memory, that enable performance and portability. CPUs are general-purpose processors and therefore are suboptimal for certain applications. Common alternatives include graphics processing units, as well as field-programmable gate arrays. As shown on the figures on the right, the advantage of CPUs is that they access the main memory directly. High-end FPGAs and GPUs usually access main memory through the CPUs, which has various complications. For this reason, our research investigates a promising future path in computer architecture, that is to integrate small FPGAs inside CPUs. In this way, FPGAs will be able to benefit from the fast access to main memory while enabling specialization. We contribute in the following ways. We propose a fundamentally new computer architecture called FPGA-extended modified hardware architecture. This architecture introduces small FPGAs into modern high-end CPUs, also supporting context switching. We provide an extensive evaluation and simulation for fine-grained reconfiguration using an operating system. Finally, we also conduct feasibility studies to check whether this approach is ready for the technology of today. In order to do this, we provide a model fast-reconfigurable FPGA and also provide extensive profiling of opcode behavior to determine the caching requirements. All our code has been open-sourced and you can find it in this link here, which redirects to our GitHub repository. We present some of the challenges in current systems. Starting with general-purpose processors, they provide a fixed instruction set architecture. This means that ISA research is needed to select the most appropriate selection of instructions to be supported. The problem is that trending applications for which instructions may be based on can be ephemeral. CPUs have attempted to approach accelerator level of performance by using single instruction multiple data instructions. However, there are many challenges with SIMD, such as with Intel's VX512, which increases power use and sometimes worsens the performance. The list of SIMD instructions in current ISAs are very extensive, including thousands of instructions. This can require considerable silicon area and power, which can be a deal breaker in many cores. On the other hand, FPGAs have their own significant challenges. Most high-end FPGAs today are based on the NUMA model, which complicates development and deployment. To name a few complications, vendors limit the programming models, such as by requiring data offloading in some cases. Abstractions like high-level synthesis try to overcome the communication complexity. However, this is problematic for systems research, as proprietary code is used and locks down the possibilities of the hardware. To overcome this, implementing open-source solutions from scratch is possible, but it is difficult to catch up with new FPGA iterations. One of the most important limitations of FPGAs for big data is the low performance to main memory, yielding an order of magnitude lower throughput than CPUs. They provide their own DRAM, but this is redundant and requires lots of engineering effort to make an efficient use of it. This can explain the fact that there are no large-scale FPGA deployments that rely primarily on FPGA's memory. Finally, FPGAs do not have easy access to CPU's fast caches, and any application that implements its own caches is considered research on its own. Now, with respect to the related work, we look at projects implementing instructions using FPGAs. One of the common limitations is that they are mostly based on embedded systems, and there is no notion of multiprocessing. Context switching is an important attribute of operating systems, and supporting it is necessary to incorporate FPGAs transparently. They are also sometimes based heterogeneous systems, such as by requiring a separate FPGA using its own instruction architecture. The most important limitation of these works is that they focus on specialization, implementation, and optimization. This provided little opportunity to propose a general-purpose architecture, as the focus was constrained by the engineering effort and the insights by the platform limitations. In this slide, we present our novel computer architecture. The new computer architecture is called FPGA-extended modified hardware architecture because it extends today's most common architecture with FPGAs. As it can be seen on the figure, this assumes a reconfigurable core with reconfigurable regions inside the instruction disambiguator. The main difference is the addition of a bit stream cache at level 1, alongside the instruction and data caches, to provide the bit streams to the instruction disambiguator. This table summarizes how the existing computer architectures compare with ours. First, the von Neumann architecture used shared caches for instruction and data, providing a relatively low memory performance. Then the Harvard architecture separated the caches and memory system for instruction and data, improving the performance such as for efficient pipelining. Then the modified Harvard architecture of today uses split caches at level 1, but unified caches and memories starting from level 2. When using an FPGA today, the bit streams are not yet considered part of the memory hierarchy, as there is little focus on making reconfiguration fast. For example, bit streams may be loaded from flash memory. Finally, on the right is our architecture, which uses the bitstream cache alongside the data and instruction caches, but unified their address space. The implementation of the instruction disambiguator is shown on the top right of this slide. As you can see, it has small FPGAs inside a cache-like structure at level 0. The input and output operands are multiplexed according to the opcode or opcode group when instructions share a bitstream. The implementation efficiency of the structure contributes to the instruction implementation hit latency. Next, we have the bitstream cache, which is a separated cache providing the bitstreams to the disambiguator. Now, why we do want a separate cache? The answer is that bitstreams have special features making them impractical to stay in data or instruction caches. First, the block size needs to be as large as 20 kilobytes, for example. In order to support fast reconfiguration, a very wide data bits is also needed, such as 2000 bits. There is also different opcode localities, and the separation can also help with an efficient pipelining of the bitstream requests. Finally, we notice that the implementation efficiency of the structure contributes to the instruction implementation miss latency, as opposed to the hits of the disambiguator. The proposed architecture has lots of advantages. First, we introduce multiprocessing support for modern and high-end processors. The notion of context switching also enables the reuse of bitstreams by multiple applications. The software can also remain agnostic to the FPGA existence. This can lead to an easy adoption, as legacy applications are still supported without any modification. This approach can give the opportunity to load custom instructions, which can be stored in an application's binary. Alternatively, the operating system could also provide bitstream libraries for desirable but less frequently used instruction extensions. This is similar to how GCC can link function calls to mathematical libraries in software. Additionally, the reconfiguration is automated by the hardware. This can make the bit streams more portable across different machines. This also helps with the latency, as there is no extra instructions for configuration, for example. Finally, as the communication circuitry is kept outside the FPGA area, smaller FPGAs are used. This is desirable because smaller regions mean smaller bit streams, lower latency of loading those bit streams, and a high operating frequency. By keeping the communication hardened, the code for implementing instructions can be kept simple and maybe avoiding the need for HLS. Before moving to the evaluation, we explain our evaluation platform. Ideally, we would fabricate a chip with a high-end CPU, but this would be very expensive at this point. Therefore, we use a RISC-V softcore called Symposium for the experiments. When there is an instruction slot miss or hit, we add artificial latency. This is done to abstract the FPGA architecture for the system's experiments, though we examine the architecture in a different experiment. Symposium is a RISC-V softcore from Imperial College London optimized for running it on an FPGA. It supports custom SIMD instructions, but this feature is not used by our study. We modify Symposium in the following ways. We add support for the F extension of RISC-V, resulting in the specification RV32IMF. RV32I is the base integer instruction set, M is the integer multiplication and division extension, and F is for floating point support. Additionally, we add some control status registers necessary to run our operating system. Note that a different subset of those registers mentioned here may be needed for newer experiments, such as with an updated compiler. The main addition to Symposium is the instruction disambiguator. It is responsible for adding the artificial latency when there is a slot miss or hit. This uses the opcodes as cache tags, but the FPGA architecture is presented on a later slide. For this experiment, we use the following compartmentalization scenario. We group instructions based on their logic similarity. This resulted in 10 groups treated as bit streams. For the M extension, we have 3 groups, one for multiplication, one for division, and one for the division remainder. For the F extension, we have 7 groups. The general idea of the experiments is to emulate an environment where a processor has no space for 2 extensions, such that M and F compete with each other for FPGA slots. This framework runs on an FPGA, though we decided to use simulation in the end, because Verilator was fast enough for our purposes. With respect to the benchmark suite, we used mbench. We adopted them for our experiments by making some changes. First, we ported the benchmarks to Symposium, such as by changing the system calls. Then, some instances of double precision floating point have been changed to single precision to be able to benefit from the F extension. A first preliminary experiment shows how the different instructions are used by each benchmark. All benchmarks here are compiled with the RV32IMF specification enabling all studied instructions. As we can see, the yellow instructions are the base ones and are more common between the benchmarks. The blue instructions are for the M extension, which also seems popular among the benchmarks, but the green for the floating point instructions are less common and are used in different combinations. Note that out of the 22 benchmarks, anything above the CRC32, which is the rightmost, has the same instruction signature. In this slide we conduct another preliminary experiment. This time is to understand how these 22 benchmarks can benefit from the different extensions in terms of runtime. In order to do this, we compile all benchmarks using the following specifications. First, our v32i is for the base instructions, our v32im has the M extension, our v32if has the F extension, and our v32imf has both M and F instructions. For this experiment, no reconfiguration is used yet, and the core specification is our v32imf, which is the superset of the above. As you can see from the figure on the bottom with runtimes, there are benchmarks that benefit significantly from either one or the other of the extensions. There are some that benefit from having both enables, but there are some that do not benefit at all, along some outliers as well. We use the same dataset to do a classification of the benchmarks using the figure on the bottom of this slide. We plot the speedup of M over the base set in the x-axis, and the speedup of F over the base set in the y-axis. This resulted in 3 benchmark classes. First, there are 9 benchmarks that are insensitive to the improvements of the M and F extensions, called insensitive. Second class includes the 8 benchmarks that only seem to benefit from M. Third is the improved by F and M class with 5 benchmarks, which is the bigger circle in the figure, with speedups reaching over 25 times. This slide presents the single program evaluation of the new computer architecture. We use the 5 benchmarks that are improved by both F and M in order to study the competitiveness of the extensions. The main question we have is whether the reconfigurable approach can perform similarly to having both extensions hardened. As a reminder, the software now uses the base instruction set without latency, but now has only 4 slots to accommodate the following instruction groups from F and M. In our experiment, we test the following configurations for the latencies on the instruction slots. We explore miss values of 10, 50, and 250. The idea for the 10 is to approach the latency of a hardened but expensive instruction, the 250 for longer reconfiguration, and the 50 to be in between. Similarly, for the hit latency we use either value or a non-zero value according to the table. Note that it is not our goal to pinpoint the exact point where the latencies make this architecture beneficial, as the scale will depend on the implementation, such as for the CPU and the FPGA regions. First, we add some baselines to our figure to give a better sense of the benefits of the approach using the different latency configurations. We have 2 baselines, one for the base instruction set without F or M, and then a series containing the maximum value between our v32im and our v32if. The latter is useful for understanding the best potential of F and M when they are featured alone. On the figure, the y-axis is the speedup over a v32imf, which features all extensions. In reality, all shown numbers are slowdowns, but the term speedup is kept for consistency. Now, we add the 2 series for the 10-cycle misses for latency. As you can see, overall they are both better than the max series. For no latency, on average, no hit latency yield 90% of the performance of our v32imf. With 1 cycle hit latency this drops to 81%. Next, we see the performance of the 50-cycle series. For no hit latency, this is similarly competitive to the theoretical max IMIF at 71%. With a 4-cycle latency, this number drops to 49%, but it is still competitive over when having only 1 fixed extension. Finally, we check a worst case for the missed latency at 250 cycles. With no hit latency, this performs similarly to the 50-cycle latency with 4-cycle hits. However, with 16-cycle hits this performs worse than having no extension at all, making it undesirable. As a conclusion, the implementation latency matters a lot, and in a later slide we will see if a 50-cycle reconfiguration is possible with existing technology. In this slide we present our multi-program evaluation. In order to support context switching we use FreeRTOS, a real-time operating system. Using the words of its creator Richard Berry, this can be seen as a multi-threading library. This was useful because it provided a minimal framework to experiment with the operating system scheduler. The porting of FreeRTOS to CMODENS involved modifying the context switching routine to include saving and restoring the floating point registers. This resulted in a single binary containing all 22 benchmarks working as threads. In order to get a performance measurement using this setup, 2 benchmarks are enabled at a time and they run again and again until we reach a certain number of iterations. Then the average runtime per run is compared to one featuring no reconfiguration. As before with our v32imf, we explore the following attributes. For the simulated architecture, we select a 50-cycle latency for misses. Here we also check a different number of slots in the disambiguator because the concurrency increases the opcode demand. Then, we also make two variations of the FreeRTOS binary, one with a 1000 cycle timer interrupt and one with 20,000 cycles. The idea is to see whether we can make reconfiguration less frequent to benefit performance. For this experiment we generate benchmark pairs as follows. First we get two benchmarks out of the class that benefits from both the F and M extensions. This results into 10 combinations. Another dataset involves pairs coming from the latter class plus one from the benchmarks that only benefit from the M extension. This results into 40 pairs. First we see the results for the interrupts of 1000 cycles and the benchmarks that benefit from both F and M. On the bottom figure, we plot with dotted lines the baselines with a fixed specification and the variations of our approach with a colored line. The y-axis is the speed up over having all extensions, as before. The x-axis represents the 10 pairs, but each series is sorted separately. As we can observe, the 8-slot performs better than the 4-slot and the 4-slot performs better than the 2-slot disambiguator, which is expected. Using these pairs, the F extension seems more valuable than the multiplication extension. Notice how the 2-slot is worse than having no reconfiguration at all, because it increases the slot misses dramatically. Then, we compare the last plot with the same experiment but for 20,000 cycles interrupts. As shown from the figure, all reconfigurable series are improved. For example, the average speedup of the 4-slot series improves from 0.62 to 0.71 of the performance of our V32IMF. Finally, we check the performance of the other pairs. The observations are similar, such that the longer time between interrupts helps performance. However, the performance is generally better than with the other benchmark pairs. When averaging these findings for 20,000 cycle interrupt and for reconfigurable slots, the approach is 3.4 times faster than having no extension, 1.5 times faster than the M extension alone, and about 2 times faster than only having the F extension. In our work we also conduct a separate study to see how feasible is our architecture using existing technology as building blocks. We target the 50-cycle reconfiguration latency from the previous experiments. In order to answer this question, we design a fast-reconfigurable FPGA and prototype it in simulation using NextBNR. This architecture has some special features enabling fast configuration. First, there is no block RAM, as we do not intend to include large states at the moment. Next, we use 4 input lookup tables because it resulted in a smaller configuration state. We also not use DSPs at the moment, though this can help in certain applications and it is part of our future work. This FPGA also supports wide reconfiguration data path to reach the target latency. In order to do that, this required more bit lines and fewer word lines, as illustrated in the figure. The new architecture is tested for custom instructions based on the RISC-V-bit manipulation extension. We have also conducted an experiment to show how the older 4-input lookup tables were beneficial in our case. The conclusions of this experiment was that 50-cycle latency was possible with the 1824-bit data path for reconfiguration. Future work includes further optimization and generalization of the internal FPGA architecture. The final feasibility experiment studies how opcodes are used in higher-end processors such as x86. This will try to answer how large the bitstream cache will need to be for providing good performance in modern systems. We achieve this with a custom Intel Pin tool that profiles the localities of the opcodes. The Intel Pin tool keeps distribution information on the unique number of instruction data in opcodes. This is done for different time slices, representing a certain number of instructions. We use Geekbench for the single program experiment and mbench for oversubscribing multiple threads on the same core. For the single program experiment, we plot the median unique count of the misses for each of the opcode, instruction and data series. We also provide the lower and upper quartiles using the shaded regions. As a conclusion, the opcode curve remains flatter for the longer time slices. This indicates longer lasting localities than data and instructions. It is also below 64 blocks, which means a smaller cache may be enough. Next, we do a similar experiment for different amounts of oversubscription of multiple benchmarks to the same core. This time the x-axis is the amount of oversubscription for the same 32,000 instruction time slices. We also superimpose the distribution information. As a conclusion, more oversubscription impacts instructions, but less so on opcodes. The median compulsory misses for opcodes remain below 64. If we construct a 64-block bitstream cache with a 12 kilobyte block size, this results to 768 kilobytes of SRAM. This is feasible with today's standards. To conclude, small FPGAs implementing instructions is a promising future path in computers. For a 50-cycle miss latency, we showed that it can approach 70% the performance of having all extensions hardened for single benchmarks, and 82% for benchmark pairs. We contributed with a novel computer architecture introducing FPGAs inside modern CPUs with context switching support. We evaluated fine-grained reconfiguration. Finally, we studied the feasibility of the architecture using existing building blocks and by profiling the opcode use. All source code is open source.
Thank you very much for your attention. All source code can be found using this link. Any question is welcome.